Okay, welcome everyone to the final seminar in the Observations and Phenomenology series of quantum gravity across approaches, or the final seminar of the season. Today, our topic is black holes and possible observations from black holes and the gravitational waves that they are emitting. And we are very happy to have Steve Giddings from the University of California in Santa Barbara with us, and Hal Haggard from Bard College, who will give back-to-back talks. Before we start, just a brief word of procedure. So the talks will take 25 minutes, and afterwards there are 5 minutes for very brief questions. And after that, we have a long time for discussions because Hal has a sharp cutoff at some point. Let us keep the discussion brief after the talks such that we have more time for the discussions. If you have questions during the talks, feel free to use the Zoom chat. We also have the option to post anonymous questions via a form that one of the co-organizers is going to post in the chat soon. And there's also a Slack channel to this talk today. So, but without further ado, let us start with a talk by Steve Giddings on quantum black holes, crisis to observational prospects. And we're very happy to have both of you, Steve and Hal, here today.
Thank you. Let me get my window set up optimally here. Okay, thank you for the opportunity to speak in this very interesting series. And as noted, I'll be talking about the black hole information crisis is one way of thinking of it. And let's just jump right in and start with the basic problem. So as we know, you can form black holes from collapsing matter. Let's think about a black hole that's formed with a radius r. And actually, let me check. Can you see my cursor okay, the pointer? Great. Okay, and then such a black hole will, as Hawking told us, ultimately evaporate over a much, much longer time scale, differing by a factor of roughly the Bekenstein-Hawking entropy. So we have a picture like that. Now let's dig into that just a little bit further into the Hawking process. And so we know what the observer falling across the horizon sees as basically vacuum can alternately be described in terms of entangled pairs. The dotted line here represents entanglement. And as that pair, which here's sort of a cartoon version of its wave function, as that pair evolves in time, one partner escapes out to infinity. That becomes the outgoing Hawking particle. And then that remains correlated with whatever the internal state of the black hole is, at least we can think of it that way. And we have a fairly concrete dynamical description of this process that we can give. But then if the black hole disappears, this outgoing Hawking particle has nothing to be correlated with, nothing to be entangled with. And so that really can't happen in a unitary fashion. That leads to, if you take this picture literally, leads to non-unitarity. So let's distill the essence of the problem in what I call the black hole theorem, or a black hole theorem. It's a very general statement of the problem, which clarifies the assumptions. And of course, if you clarify the assumptions, that also clarifies how you can get out of the basic logic. So the statement is that the postulates, the following postulates are inconsistent. First, quantum mechanical unitary evolution. Second, the statement that a black hole is a subsystem of a bigger system. For example, one way of describing that would be to write the Hilbert space as a tensor product. The statement that black hole states have identical exterior evolution, which we actually see in the field theory approximation. And finally, the statement that a black hole disappears at the end of its evolution. So those postulates are inconsistent. That's the basic statement of the theorem, which we just illustrated with the picture. A couple of notes. First of all, the statement that we have subsystems and that black hole states have identical exterior evolution can be illustrated by explicitly looking at the local quantum field theory evolution. But those are more general statements, which we might expect to be able to make in some more general framework for quantum gravity. Secondly, though, there is a question of how to formulate the notion of a subsystem sharply in quantum gravity, and I'll come back to that. But this is such a deep conflict, a deep problem, that it suggests that it is an opportunity for quantum gravity. It could be an important guide for the principles of quantum gravity, and has the flavor perhaps similar to some of the crises that led to the formulation of quantum mechanics, such as the crisis of atomic stability. So what are we to make of this? Well, there are many proposed alternatives for what the resolution to this crisis could be. And I'll just start out by enumerating some of those. And then what I'm going to do is talk about what the objections are to each of these, and we'll try to more carefully understand what could be a reasonable way out of all of this. So, of course, the first thing that was postulated in all of this was by Hawking, that we have fundamental unitarity violation. So that's a violation of postulate 0, quantum mechanical evolution. It was, of course, later realized that this leads to drastic violation of energy conservation that would be basically in contradiction with everything we see. So that looks like that is a non-starter. A second possibility is that black hole evaporates down, but then leaves behind a microscopic remnant, say of order of the Planck mass. And so that would violate postulate 3. That's still a scenario which is being advocated by some folks in the loop quantum gravity community, Ravelli and others. But the essential problem with that is those kinds of objects would have a huge number of internal states, unbounded in fact, and that leads to unbounded production instabilities. Now that's a separate discussion that I don't want to have here. There isn't time for it, but some of the references where you can pick up threads of that discussion are given here. So actually I'm going to use some color coding. Dark red means that these look like they are just, well, these are very serious objections which make the scenarios look like they just aren't viable. And then I'll use magenta for, this is an interesting question still to pursue, roughly speaking. Okay, so let's move on down. Massive remnants. So the basic idea here, which was enunciated some time ago, is that a black hole at some point transitions into some kind of new stellar remnant at scales where the mass is much, much larger than the Planck mass. And so, you know, we can think of this as some new exotic thing. We know of stellar remnants like white dwarfs, neutron stars, and so on. This would be some kind of new stellar remnant. That's going to violate, well, postulates 2 and 3. And there have been many examples given in the literature subsequently of objects that are purported to, you know, fall into this kind of category. So, for example, there is the Gravastar scenario. There are fuzzballs where it's imagined that there is some exotic states of excited strings and branes in higher dimensional geometry just outside the would-be horizon. The notion of firewalls, where you would have a very high energy, say, curtain of particles that are present just outside the horizon. And of course, the one of the Planck star scenarios. Now, the objection here is that we don't really have a good description of the dynamics of any of these. And it looks like any such dynamics is going to have some non-local properties, at least as conventionally formulated. Okay, so moving on, another possibility is the nonviolent unitarization idea. That would violate independence of the external state. I'll come back to that. I'm going to talk more about that. But again, that involves some kind of non-locality. And then there's ER equals EPR, which looks like it would violate at least 1 and possibly 2. A question there is there any really systematic account of how ER equals EPR fits into some bigger story and resolves the problem? And certainly it looks like that would involve some new non-locality on scales much, much bigger than the event horizon size. Then, of course, there's been all the excitement about replica wormholes and the page curve. And one possible idea is that those replica wormholes are associated with, so to speak, real wormholes, emission of baby universes. And so how would that fit into this logic? Well, At least that looks like that might violate usual quantum mechanical rules, at least in our universe, as well as the postulate that the exterior state is independent of the interior state of the black hole, due to, say, new interactions induced by these emission of these baby universes. But although there's been a lot of interest in that discussion of the page curve, really what we need in this story is an actual description of the quantum amplitudes in a more complete account. And it looks like one will need to involve at least what looks like some known locality with respect to, the space-time in which the black hole lives. And then finally, there's the possibility that the subtlety of gravitational subsystems is so important that it resolves the problem. That there isn't such a sharp definition. And that really goes back to the quantum Hare discussions, Hawking, Perry, and Strominger. There's been some other more recent discussion of this question. There actually is a real question of defining subsystems in quantum gravity. And it's true that small effects do spoil one approach to a definition of such subsystems. But in fact, those effects are exponentially small, and it's not clear that they are really sufficient to resolve the problem. In any case, that's a very important question for further discussion. I've given one reference where I've looked at some of these issues, but I'll just end up by saying that we have at least an approximate perturbative definition of subsystems, and it's plausible that any effects sufficient to resolve the crisis would involve some new non-local physics. So those are the essential alternatives. And a common thread among these alternatives, at least the ones that remain possibly viable, is that they involve new gravitational physics at scales of order of the event horizon size or larger, not just at the Planck scale. Now, of course, the conventional wisdom in quantum gravity is that's crazy. We only have quantum gravity effects becoming important at the Planck scale. Although, you might have used the same logic if you imagine being a classical physicist before quantum mechanics was invented. And, what's this idea of new physics taking place out at the, say, atomic scale, at the scale of the Bohr radius? That doesn't make any sense from the existing formulation of classical physics, which you would have. So likewise here, this conventional thinking may be basically too limited. But in any case, I'll make the empirical observation that this is actually now a near community consensus that there is new physics. We just haven't agreed on what it is at the event horizon scale. The fuzzball story, the firewall story, the gravastar story, the Planck star story, nonviolent unitarization, ER equals EPR, replica wormhole, subsystems failure, all involve some new important quantum effects taking place at the Planck's, not at the Planck scale, at the event horizon scale or larger. So that's the first observation. We really seem to be talking about that kind of thing going on. And then, of course, we have the newly available electromagnetic and gravitational wave observations taking place at that scale, which have been very exciting, one of the most exciting things to happen in black hole physics in recent years. Of course, by the Event Horizon Telescope and LIGO, Virgo, and Haggard. So putting these together strongly suggests, if we're expecting some new physics on the event horizon scale and we have new observational windows, we should be looking for observational signatures. And so let's just start out by briefly touching on the massive remnant kind of scenario and talking a little bit about how you might look for observational signatures there. So again, the idea is that you have some hard modification of the standard black hole picture where the would-be event horizon is replaced by some new kind of object which extends out, say, a distance delta RA from where the event horizon would have been. And so, in fact, you can parameterize such objects by some effective phenomenological parameters, the height of this sort of atmosphere, you could call it, above the would-be horizon, the hardness scale, which represents the typical momentum or hardness for scattering, momentum transfer, and then you could come up with other parameters. And some discussion of sort of phenomenological parameterizations appears in various references. And what can we say about these scenarios depending on what those parameters are? Well, first of all, it's absolutely clear that we've already ruled out, some such scenarios, because if we had some new kind of, stellar remnant, which was much, much bigger than the event horizon size, than the Schwarzschild radius, that would not produce the kinds of images that we are actually seeing. For example, now the image of the apparent black hole at the center of our galaxy. So certainly massive remnants with sizes much larger than the event horizon size are ruled out. The natural scale to think about is where the size of such an object is of order the Schwarzschild radius. And there we, of course, expect to have some observational sensitivity, but it's a more subtle question. We could try to understand what we can and can't rule out through electromagnetic images, gravitational wave reflection, tidal distortion, say when you're inspiraling, and so on. Just a note, there's been a big industry along these lines where many quantum field theory models of exotic objects have been considered, but it's not clear how they really address the crisis, although they do serve the purpose of being possibly useful for illustrating, sensitivity to modifications of the standard black hole picture. Okay, and then of course we could think about a situation where the new object has a size, maybe it's just a Planck length outside of the would-be event horizon, like in the case advocated in the firewall story. That we expect to be harder to see. You might imagine having something like a hard surface just outside the would-be horizon, which you think of as a membrane, but it's very deep in the gravitational well, and for example, you might expect it doesn't really affect the light images. Although it has been argued that there is possible sensitivity due to, for example, gravitational wave echoes. So here are some of the folks who have been involved in that discussion. And the basic picture would be you form, instead of a black hole, one of these new kinds of stellar remnant, or new kinds of remnants. Of course, you would need prompt formation of this kind of object. If you initially formed a black hole and a later transition to this kind of remnant, this kind of hard object, that isn't something that we could bound. But if you have prompt formation, then the gravitational waves from the formation, some of them will be, will, roughly speaking, fall into the gravitational potential, but then they can be reflected off of this membrane, and they can actually exhibit a bouncing phenomenon off the angular momentum barrier with some transmission at each bounce. And so you can get these, so to speak, gravitational wave echoes, where you get an echo of the signal from formation. And so that's something that has been looked for. And in fact, there have been conflicting conclusions discussed in the literature. It's been looked at, well, in various references, and I'll just leave it at that. But this is one way of exploring the possible phenomenology of such things. And really more study is warranted. But just coming back to a general observation, in general, what is needed in this story is more careful discussion of consistent dynamical models. I'll come back to that, but so we can actually make predictions. So the massive remnant scenario, which I've just illustrated, represents a rather drastic modification of the black hole picture, some fundamentally new kind of thing without a horizon. And one important question is, could there be a more subtle modification of local quantum field theory that actually resolves this crisis? Something that's closer to respecting the classical equivalence principle. And what I have in mind is, is there a modification of the story that still essentially looks innocuous, say, to an infalling astronaut? An infalling astronaut maybe only sees some small effect. And this is the central idea behind nonviolent unitarization. Here are some of the references. I've sort of been developing this picture over a number of years. And so let's, in fact, go back to this black hole theorem and to our assumptions that get us into trouble. And in particular, if we take 0, 1, and 3 seriously, which I think makes some sense, then we might question, however, number 2, which essentially is related to the traditional statement of what locality is. The statement that black hole states have identical exterior evolution. And so in fact, let's parameterize in a principled fashion some violation of postulate number 2 and assume that the other postulates are still viable. So we're just going to parameterize our ignorance in a principled fashion. This can be a very powerful thing to do. So let's think about Hamiltonian evolution, and you can write down the Hamiltonian for, say, evolution governed by local quantum field theory in a black hole background. We've done that, a careful job of that, for example, at least to leading order. But then you can think about what kinds of corrections that must receive if the problem is going to be resolved. So you expect there to be sort of big corrections to the Hamiltonian interior to the black hole. Let's not focus on those, but also you need some kind of correction, which you might imagine could be small to the Hamiltonian, which basically accomplishes this transfer of entanglement from the black hole internal state to the exterior, or in other words, makes the exterior state dependent on the state of the black hole. So we'll call that delta HI. And the simplest example of an interaction which transfers entanglement in that fashion is something where you have an operator that acts on the black hole states. Let's just take a basis of such operators, label the black hole states this way, and then times an operator that acts on the environment. And so we'll try to parameterize what these interactions could be in this form. What kinds of operators might we involve here acting on the environment? Well, to make a long story short, the universality of gravity along with approximate locality suggests that you consider a special kind of operator, which is basically something just coupling to the exterior stress tensor with some what I'll call form factors that depend on the, well, basically include some of the couplings and depend on the black hole state. So again, just parameterizing our ignorance, but with some simplifying assumptions, we have an operator that looks like that. We can reorganize that by writing the interaction term as an integral against the stress tensor of this thing, which I'll call H, which is the combination of the basis of operators acting on the black hole states and the form factors. And so this, again, is an operator which acts on the black hole Hilbert space, so to speak, the space of black hole states, but it looks like a metric perturbation. So it's behaving like a state-dependent metric perturbation. And then finally, what else can we say about the properties of this operator? Well, in a typical black hole state, you might expect that the variation of this operator or its expectation value is on scales of order the event horizon size. That's a naturalness assumption rather than varying, say, on Planck scales, which would produce very high energy particles, et cetera. This is the natural scale that we have in the problem. And then finally, this contribution to the Hamiltonian needs to transfer information at a large enough rate to basically restore unitarity. One way of achieving that is if the expectation value of this operator is of order 1, that's like having an order 1 perturbation to the metric, that clearly would suffice if it's varying on these scales. That's what I'll call the strong scenario. But actually, it looks like you don't need that large of a coupling, so to speak, for the following reason. Let's think about a transition induced by this Hamiltonian, this correction to the Hamiltonian, a transition of the black hole. Roughly speaking, the information transmission rate is equal to the rate at which you undergo such transitions. And that's given by the, by Fermi's golden rule, which involves the density of final states times the typical matrix element of the perturbation to the Hamiltonian. And that density of final states includes this huge factor from the number of black hole internal states. And for that reason, you can have typical matrix elements which are exponentially small and still get an order 1 information transfer rate, which is what we want. So that's the, so to speak, weak scenario where also the expectation value of H in a typical state would likewise be exponentially small. Now, I'm often asked, where do such effects come from? What's the idea behind them? Well, one idea right now, at least, is that we're just parameterizing the failure of the accuracy of the classical description. You might as well have asked a classical physicist to explain where the effects that stabilize the atom come from. You could try to parameterize those like Bohr did, but really you need to invent quantum mechanics and understand it before you understand what is stabilizing the atom. You can parameterize the physics, but not really describe it in classical physics. And so that is at least one idea for how to think about this. What about observational signatures? Well, in the strong scenario, if we really do have what are effectively order one perturbations to the metric, that could lead to, that are time dependent, that could lead to possible time dependent distortions of the black hole image. And that's something where Demetrius Saltis and I looked at models for that, just simple models, and found that it's true that you could get, in fact, quite significant distortions of the kinds of images we're now seeing with the Event Horizon Telescope. So for that reason, some ranges of parameters in these strong scenarios are ruled out clearly by the Event Horizon Telescope images that we're seeing, although I don't think anyone's carefully looked at what parameters are ruled out, what ranges are ruled out. However, in the weak scenario, you don't expect to have a large correction to the electromagnetic image. And you might think all hope is lost until you think about the phenomenon of gravitational wave scattering off of a black hole in the presence of these new interactions. And you realize that the contribution to scattering, say from a state alpha to beta, again, will be governed by the same kind of formula, Fermi's golden rule, where now we have a matrix element between the initial and final gravitational wave state. And you have the same kind of scaling entering into the matrix element there and into the density final state. So you can get an order one correction at momentum transfers of order one over the event horizon size. You can get an order one correction to gravitational wave scattering. So that tells us that gravitational wave absorption and reflection can be modified by this kind of interaction term. And that means that we have corrections then to gravitational wave signals that would be produced from, say, inspiraling black holes. So that's something where we're investigating that further to try to turn it into a more careful calculation. But just from this basic logic, you see that there's a real possibility there. So just to finish off, since I'm about out of time, the logic of the black hole theorem constrains and characterizes possible resolutions to the crisis. Anyone who has a proposed resolution to the black hole information problem or crisis should really consider the observational possibilities that that involves. Of course, a key question is, finding a better description of the quantum dynamics, or we really need better developed dynamical models to address this kind of question. That's, I think, something folks should be striving for. For example, with the large discussion about replica wormholes, an important question is, what is the associated dynamical description of amplitudes for, say, evolution of a black hole? And already some very general scenarios are ruled out. Large massive remnants. Some of the echo models look like they're being ruled out. Strong nonviolent unitarization with certain parameters. There is still this important basic question in quantum gravity: is a black hole a quantum subsystem? Can it be thought of such a subsystem? And that warrants some further study and discussion, which we could try to have later. And if so, if that is true, then we can parameterize minimal interactions for unitarization in an effective quantum theory. And these can, in particular, influence gravitational wave or electromagnetic signatures. So thank you very much. And I will just leave you with some further background reading.
Yeah, thank you very much, Steve, for this great overview talk. We have a brief moment of time for quick questions or quick understanding questions before moving on to the next talk. If there are any questions, please raise your hand in Zoom now. And just as a comment, for more discussions, for longer arguments, we have a whole discussion session after both talks. So right now I don't see any hands. So maybe it's best we just keep on going because Hal has a time cutoff and then we have more time for a joint discussion. So thank you again, Steve. We'll come back to you after Hal's talk.
Okay, thank you.
Okay, yeah, great, Hal. We can see your screen and also your cursor. So let's go on with our second talk by Hal Haggard about random geometries, gravitational waves, and the black hole spin puzzle.
Thank you, Sebastian. Thank you, everyone, for being here and for this kind invitation. I really enjoyed Steve's talk. It's a very general, broad overview of all of the ways that he's encountered and other people in the gravity literature for thinking about this observational question. I'm taking a complementary approach. I'm going to be focusing on one example, very specific, and trying to go all the way to connecting it to gravitational wave observations. There's plenty to say about this, and there's plenty to develop further, but I think it is really interesting to see some of the challenges that come out of trying to connect directly to the gravitational wave data. So that's why I'm going to go into that in some detail. So my talk is also different in the sense that I'm looking at an effect that is very robust within different approaches to quantum gravity. I just want to investigate the black hole entropy formula, the Bekenstein-Hawking entropy that Steve was mentioning, and to ask, well, we see all sorts of quantum theories of gravity giving rise to this formula, but do we have any observational evidence for it? And can we garner some observational evidence for this formula? So in pure classical general relativity, a black hole is completely characterized by just two parameters, its mass and spin. But in quantum gravity, we claim it has a huge entropy given by its horizon area in Planck units. And that huge number of states, the question is, where are they encoded? And can we actually claim that they're there? Different approaches have different ideas about that encoding. I also just want to remind people of a simple dimensional claim. We often hide a lot of the dimensions in the black hole entropy, but I find this formula to be just remarkable in the way that it brings different areas of physics together. In Newton's constant, you see gravity. In Planck's constant, you see quantum mechanics, special relativity. We always suppress the Boltzmann constant, but that shows that thermodynamics are here. And geometry, the area of the horizon coming all together in the single formula. So that's a really striking thing to me, that it brings all these different areas together. In particular, I'm going to think a lot today about gravitational thermodynamics and general relativistic statistical mechanics. And I want to emphasize that they're really atypical. So gravity is a long-range force, and we can't shield it. At least nobody has a very practical method for experimentally shielding and isolating a gravitational system. That's an experimental way of saying what Steve was saying about how do we decompose our gravitational field into subsystem. Strongly gravitating systems like black holes don't have additive energies. The theory is nonlinear. And I think this is really interesting when you think about things from the thermodynamical perspective. Thermodynamics, one of the things we build up the theory from is the extensivity of certain observables. So when you take two subsystems, you put them together, the energy just doubles if they're the same, right? And that extensivity, we can't have it in gravity. We know we can't have it on principle. And that means that the thermodynamics has to be different. On the other hand, from my perspective, thermodynamical or statistical mechanical arguments are the most promising way to look at quantum gravitational phenomena observationally. So my first question for Steve when we get to the discussion session is going to be, which of these observational windows does he think is most plausible, most accessible? And from my perspective, I think it's gonna come from a statistical mechanical insight that we have, much like blackbody radiation was one of the early keys to quantum mechanics. So I want to illustrate this very briefly with a very simplified example, just that of a self-gravitating gas. So a self-gravitating gas, if you let it come to equilibrium, it virializes. And as you remember, the virial theorem tells us that the potential energy in the gas is negative twice the kinetic energy in the gas. So if you add these up and get the total energy, you see this really interesting thing that the kinetic energy, which would be characterized by the temperature, and the total energy have opposite signs. And so if we use equipartition within that result, we see that the total energy actually goes with negative 3/2 nkt. And this is a very simple, immediate way to see the negative heat capacity of gravitating systems. So a way of understanding this is that gravitating systems naturally tend to clump, and we see the same negative heat capacity in black holes. And so I just really want to emphasize that these are not your standard thermodynamic systems. So that makes them very interesting to look at observationally, and gravitational waves are a promising way to do that. The LIGO, Virgo, now Cagra collaboration, these are the sites around the world. And what I want to do is encounter these ideas with those observations. Sorry, I lost the advance. All right, so quick outline. I'm going to tell you about black hole formation. This audience knows it well. I'm just going to overview a few things and a few of the experimentally known things. I'm going to tell you about our idea of a mechanism for which black holes might be created without spin, and tell you a little bit about how you might be able to observe that in gravitational waves. There's a rather longer theoretical argument behind what we're doing, which is from the statistical mechanics of random geometries. I'm probably going to have to shorthand that last piece, but I'm happy to go into it more in discussion. So you all are very familiar with the standard story of gravitational collapse. The nonlinearity of gravity actually leads to this self-reinforcing, where if you get a dense enough region, even the pressure to hold up the gravitating system is creating more energy in the system, creating mass that then leads to a collapse. But the Nobel Prize just 2 years ago was awarded to Roger Penrose in part for the observation that you might worry that a lot of our theoretical models are overly simplified in their spherical nature. But Penrose worked out the fact that if you perturb the system, if you make it more generic than the spherical collapse, it's still going to be a generic outcome that you form a black hole in the process. In general, it's going to be a rotating black hole, and that's what I want to kind of focus in on now. So here are some of the observations of Xray binary systems. So these are black holes that we know about through electromagnetic radiation. 2/3 of all stars are part of a binary pair orbiting each other. And often one of the stars can supernova and collapse to a black hole. And we can see that black hole accreting its partner star on in the X-rays. So I'm going to switch to the more standard general relativistic parameter, this A parameter, which is just a dimensionless measure of the black hole spin. That dimensionless measure is trapped between 0 and 1. So this is not a complete list of X-ray binary black holes, but it does include the spin data, and it's very interesting to see both the mass ranges. So this is the mass of the black hole member of the pair in solar masses, and the spin parameters. And you can see that these X-ray black holes, they have a wide range of spins going all the way from, 0.12 up to something greater than 0.95 in Cygnus X1. So I want to ask whether we should expect to see the same sort of thing in LIGO black holes, and whether there's other populations that might be interesting. At this point, I really like to emphasize that one of the first things that we've observed in LIGO is a very unexpected mass range for the black holes that were observed. I think somehow the history gets lost sometimes in these discussions. Nobody expected that the first thing that LIGO was going to detect was 20 to 80 solar mass black holes. No one was saying that. They were emphasizing the fact that they were going to see neutron star mergers and that they might see black holes created in that process. But there were no predictions that this would be the mass window that we would open up with gravitational waves. And it's turned out to be the predominant signals that we've seen in LIGO. So I'd like to ask about this population of black holes and see if there's something interesting about it. So this is joint work with another quantum gravity person, Eugenio Bianchi, and two LIGO collaborators, Anuradha Gupta and Satya Prakash. The initial idea for the proposal, Eugenio and I proposed in an article back in 2018, and then we collaborated with the LIGO scientists to try and encounter this idea more directly with the data. As I said, I want to think about these black holes thermodynamically, so let me fix a thermodynamical context. So I'm going to be taking a sort of microcanonical picture. I'm going to fix a region of space-time. I'm going to think of the black hole as being contained within that region, and I want to fix the total mass energy of that region. So that's like fixing the overall energy, and I'm going to be in a microcanonical picture. Well, then let's look at the Bekenstein-Hawking formula in this setting. If I fix the mass and I consider spinning black holes, we can write out that, that Bekenstein-Hawking entropy in terms of the horizon area, in terms of the dimensionless spin parameter I was just explaining, and the mass ratio of the black hole mass to the Planck mass. And the observation that I want to focus in on that I find very interesting is to just plot this Bekenstein-Hawking entropy as a function of the dimensionless spin. And what you see immediately is that the entropy falls rather dramatically as you spin the black hole up. This is just a direct consequence of Bekenstein-Hawking. But I find it very interesting. It means that the highly spinning black holes are less entropic. So we use this to actually think about and write down an ensemble of black hole states. So consider the number of microstates associated with that entropy. It's just the exponential of the entropy. And the number of microstates that have a fixed mass. That is, I'm going to keep the mass fixed, but integrate over all spins. And we can build a probability of a particular spin given the mass. So the subscript here is a conditioning. I'm giving the mass. We can build a probability distribution by considering the ratio of these two numbers of states. And the thing that's fascinating about this probability distribution is that as soon as a black hole becomes even a little bit more massive than the Planck mass, this distribution becomes extremely highly peaked. So here I'm showing various contour plots for different given masses. So 2 times the Planck mass up to 20 times the Planck mass. And you see even in that range of 10 Planck masses, you get a much more peaked distribution. And by the time you get up to something like a solar mass, the average value of the spin in this distribution is 10 to the negative 38 as a dimensionless spin parameter. So if you are able to make black holes according to a microcanonical distribution, then you should expect that those black holes will have completely negligible spin. All right. This is in contrast with different models that are suggested in the literature. We call them P1D and 3D here, isotropic formation and aligned formation. I'll discuss those more in just a moment. So the questions I want to focus in on then are some black holes born spinless? Is zero spin evidence for the statistical nature of black hole entropy? And what comes of confronting these ideas with gravitational waves? So that last question motivates me to try to parameterize the gravitational wave data for you in a way that's digestible. So I'm going to treat it as an in-out process, where the in data are the mass and angular momentum of the first black hole, the mass and angular momentum of the second black hole, and the orbital angular momentum of the pair. If the pair merges, they then form a final mass with a final angular momentum and let off gravitational waves in that process. I've again recorded the dimensionless parameter here just so you can look at it. And it turns out that in gravitational wave data, it's much more accessible to look at what's called chi-effective. Chi-effective is conserved in a binary system to second post-Newtonian order. And so it's something they can much more easily extract from the cycles of the data that they have. So what is chi-effective? You can think of it as a mass-weighted average of the spins of the progenitor black holes projected onto the orbital angular momentum. So of course, the progenitor black holes can be aligned with the angular momentum or anti-aligned. Their spins can be anti-aligned. So this can range in over -1 to 1. So this is the parameter space that's most easily accessed. And I'm just going to start to slowly add on some of the LIGO data. Here are the first 3 events, the events that were measured in 2015. And there's some things you can already see. They tend to cluster kind of between a final spin of 0.6 and 0.8. And they have chi-effective rather small. And if we add more data, that pattern continues. You still see a lot of them with final spins in this range and still clustered around small chi-effective. So the question that I want to focus on then is, what does it mean to have a zero chi-effective? I don't want to be confusing here. It does not mean that the constituent black holes are zero spin. The constituent black holes each have a spin parameter, and it's certainly possible to get a zero chi-effective if, for example, those 2 angular momenta were to cancel each other out, or if those 2 angular momenta were in the orbital plane of the binary system, so that the projection onto the angular momentum, the orbital angular momentum, killed the thing. So there's at least 3 ways this could be zero. One is that each of the constituents isn't spinning, another is anti-aligned, and another is in the orbital plane. All right. So to make the comparison with this probability distribution I was describing for all of you, I want to see what we would predict if we drew from that probability distribution. So I already told you that probability distribution favors extremely small spins for the constituent black holes. But now let's actually let them merge and see what happens. So as a first example, I've taken 2 equal mass black holes, both of them non-spinning, and I've used numerical relativity to let them in spiral and merge, and I found the chi-effective and the A final for that merger. It turns out this value of 0.69 is extremely robust. If you're a nearly circular orbit and you have low spin input, you're going to get 0.69 always. So that's a very interesting numerical relativity fact that I think should be explained by theory, but I have never seen a theoretical argument for it. You can, of course, change the mass of one of the black holes. So this is usually described via the mass ratio, which is the larger black hole's mass divided by the smaller black hole's mass. And what you find is you let that kind of pair in spiral, you tend to come down on the final spin axis. So the lighter colors are larger mass ratios in this plot. I plotted something like 500 of these, and they're all overlapped on that line. But I'm going to consider a second scenario, which is that we've seen now that if you let 2 spinless black holes merge, they form a black hole with spin 0.69 in general. And that spin is going to be almost isotropically oriented. It's got mostly to do with the orientation of the orbit. So you can also consider what are sometimes called hierarchical mergers, where you merge a first generation black hole, which could be spinless if you drew it from our probability distribution, with a second generation black hole, which should have a spin of about 0.69, say, for equal masses. Here, because it's second generation, you're almost certainly going to have some kind of mass ratio going on. And so what we've done is plot, again, 500 numerical simulations of such systems. Darker is more closely equal mass ratio. Lighter colors are unequal mass ratios. And we start to fill out this kind of prediction. So this is what we did practically, and we start to compare it with the gravitational wave data here. And so here's the full GWTC1, the first 10 or 13 events plotted together with the prediction that you get from our probability distribution, which was derived from the Bekenstein-Hawking entropy. So this started to intrigue us and made us wonder if this idea had some potential. Here I've gone up to the first 3 events from run 3. So that's the run that was just completed. These are from O3A. So these are just the first 3 events. And here you see some really interesting things. Much larger mass ratios were found. GW 1908-14 has a mass ratio of about 10. So I've extended our simulations down all the way to mass ratios of 10 and added the other 2 events as well. The blue shaded region shows you those events that have mass ratios between 1 and 4. And this sharp curve at the edge was an interesting thing that we were noticing from the numerical simulations. And it's a first generation, second generation merger always stays within this this sharp edge. So here's again the stellar graveyard with now those first 3 events from O3 included and that large mass ratio event here. Okay. But how does this proposal compare to other astrophysical formation mechanisms? So there are 2 other mechanisms that are discussed a lot in the literature. One of them is called isotropic or dense stellar environment. So this is like a globular cluster where you have a lot of stars and black holes can form in that globular cluster. Because it's such a dense environment, there's no expectation of those spins of the constituent black holes being in any direction. So I'm going to call that an isotropic distribution. The spins of the constituent black holes can point in any direction and they have no relation to the orbital angular momentum. On the other hand, there's what's called a common envelope formation where you have a large disk and the 2 members that were going to eventually form black holes were formed in that disk. They're all co-rotating, and so the spin of the constituent black holes and the orbital angular momenta tend to align. So again, here are the first events from the GWTC1, and they're plotted together with the isotropic distribution in purple dots and the aligned distribution, again, from numerical simulations in orange dots on the right. And this starts to be an interesting comparison. So what I want to emphasize here is that we are not claiming that, that we think that all of the LIGO black holes are formed according to this microcanonical distribution. What we're interested in is whether a subpopulation of the total population might be drawn from the microcanonical distribution. And so it starts to become interesting whether we can distinguish populations. So by I, which is a very dubious way to go, we see that the aligned model, it certainly can't do a great job of explaining all the LIGO data. The isotropic is more compelling, although there are these large mass ratio events interestingly sort of stand out. And if you allow me both first and second generation mergers, this distribution has some compelling features to it. Okay, so as I predicted, I don't think I have time to go into the full theoretical argument here, but let me just very briefly say a few things. As I said, I don't expect that all of the LIGO black holes are drawn from this microcanonical distribution. So what are the candidates? The candidates would be black holes, primordial black holes, formed during phase transitions in the early universe. The idea would be that modes exit the horizon during inflation, and then during the radiation era, they re-enter. And if you had a large fluctuation in density, and that large fluctuation entered its own trapping radius, you could collapse a black hole. if that happens during a phase transition, well, during a phase transition, the equation of state softens, and this becomes exponentially more likely. And so the QCD transition is a very interesting case of this, where the equation of state gets much softer and you get a much more potential for primordial black hole formation. A fascinating back of the envelope calculation that I won't take you through gives the mass scale you would predict from this QCD transition, and it turns out that it's right in the LIGO window, 25 solar masses. So that's very interesting. In fact, people in the lattice QCD community have picked up on that and have done simulations that are much more detailed and rich, and they find a mass range between 0.1 and 100 solar masses as a potential range for such black holes. I already described this idea. We're thinking of fluctuations. And the key idea behind our microcanonical distribution is that perhaps if you took a quantum state of the early universe and asked for the probability of a given metric given its total energy, well, that quantum state, we don't know it. But since we're fixing the energy, it's like we've put this microcanonical delta function into the probability distribution. And so long as this primordial state is sufficiently constant over that mass shell, this reduces to the Boltzmann distribution that I was describing above. And so this produces a microcanonical distribution for spins. So this, I think, is a very interesting idea and teases general relativistic stat mech in an interesting way. So I built up the story of how we arrived at this distribution, and it's very interesting to confront it with what's happening right now. The LIGO community is very actively discussing the question of whether there's a subpopulation of zero-spin black holes. Just last year, Galadauge et al. Reanalyzed the GWTC3 data, but they allowed for a subpopulation of zero spin, and they found that indeed they populated a large fraction of the total population with zero spin black holes. Their way of parametrizing the two populations was very strict. They put a delta function on the zero spin population and then a Gaussian on the rest of the population. And that's led other people in the LIGO community to question this result on the left here. So there's a paper just from this month by Callister et al. That reinvestigates this with a much more flexible parameterization of the two populations. For example, using two Gaussians, a Gaussian distributed on zero chi-effective and a Gaussian distributed away from it. And so what you see on the right here is their probability density function for zeta, where zeta is the fraction of the population that has zero spin. And you can see that they have some support for the fact that there's no black holes that have zero spin, but each of these posteriors peaks around between 0.25 and 0.4. That is 25 and 40% of the population of LIGO black holes being zero spin. So from my perspective, this is already fascinating. There are very few astrophysical formation mechanisms that create black holes with zero spin. And so even if it's 25 or 40% of the total population, we have something to explain here, and I think it's really interesting to try and do so. Here's the full GWTC3 catalog with all 83 binary black hole mergers, 7 neutron star, maybe black hole, maybe neutron star mergers. You see the data in these blue. This is showing, again, the mass ranges. And I built things up slowly just because it's kind of fun. So I'll show you, again, our distribution with all the O3 data plotted on top. I've used the black markers again for the initial LIGO run, but I've overlaid a white marker for every black marker. It's the same event, just in the third catalog. And so you see this is the distribution. There are clearly things that fall outside of our distribution. These could not be explained by first generation, second generation merger. So let me also compare it with the isotropic population. So again, it looks like these are more likely to be captured by an isotropic sort of formation mechanism. But I still think that there's a very interesting comparison here. Thank you, everyone.
Yeah, thank you very much, Hal, for this very nice discussion about this potential distribution of the black hole spins. For the sake of time and maximizing the discussion, maybe we should just kick off the discussion and then slowly start gathering people who want to ask a question. And maybe because Hal, you already posed a question toward Steve, basically that you think, Hal, that thermodynamic and statistical arguments are a very good chance of detecting or making observational or making observations about the quantum nature of gravity. So maybe Steve, we can get you into the discussion.
Yeah, so Steve, my question for you is, of that, you did such a nice survey of all of these ideas, and I was curious, amongst all those ideas, which you find most promising?
Well, I think it's fair to say the most promising thing is the thing, in my view, is the thing I'm working on. But, this notion that there need to be corrections at the event horizon scale, but that they should not be a big departure from the general relativistic picture of black holes, I think is one really worth pursuing. And so, that's why I've been trying to parameterize, say, small corrections that are sufficient to restore quantum mechanical evolution. And so I really do view that as a very promising avenue. Now, in terms of how that connects to observation, I gave a rough outline, but I think that is, to me, the most intriguing possibility for observation. Some modifications to the gravitational wave signatures, say, of in-spiral, or well, of coalescing black holes. It's interesting to also think about that in the context of cosmology. One of the challenges of cosmology, as always, is that we have a lot of history intervening between whatever went on, say, early in the universe and now. And it's always hard to disentangle, features of that history from features of, say, primordial distributions and so on. So anyway, so that's where I'm kind of putting my my money at the moment is, can we find signatures, say, some new signatures with gravitational wave observations of coalescence?
I was also curious, you went to what you were calling hypothesis 2, the black hole states having identical exterior evolution, as the first one you questioned. But the black hole subsystem question strikes me as so rich and interesting. I was curious whether you really favor questioning 2 over 1 or not.
Well, they are kind of related, but I think that there's more than could be said today, clearly, but we've carefully looked at the question of there being subsystems in gravity, and at least there is an approximate, to a good approximation, perturbative notion of subsystems. And the basic idea is there is that you can have a lot of states in a region, but with an identical gravitational field outside. In fact, the gravitational field outside, by the constraints, only has to capture the total Poincare charges of the stuff in the middle. And so that's the information you sort of have to have when you measure the gravitational field. You can always measure the total Poincare charges of the stuff, in a small region, but you don't have to necessarily have access to the details of the quantum state. So that's the idea for how you can start to describe quantum subsystems in gravity. Now, there are subtleties in that, and that's important. I think it's important to really understand that properly, and there have been various arguments. But the fact that we do have sort of a beginning of an understanding of that, I think, is promising. And the fact that in general in quantum systems, having subsystems as part of the basic structure, usually for most other quantum systems also suggests that that might be a structure we want to have sort of there to begin with. So but anyway, I think they're both interesting questions.
Okay, I don't see any questions from the audience yet, but if you have questions, please raise your hand. Okay, now I have the problem that we have two organizers who want to ask a question. So maybe we let Elle go first, because they had the first question, and then it's you, Aaron.
Okay.
Please, all others, raise your hand. We have time for questions.
Thank you. It might be very trivial, but Hal, you were showing these different distributions for the possible spins of the black holes. And actually all three models were doing kind of a diagonal line there. Is there some underlying principle why all of them would be doing that, or?
I suspect that it's again this issue I was mentioning of mass ratios. So the mass ratio tends to push you down on your final spin. So so I think in all three distributions, that's what you're primarily seeing, Elle.
Great, thank you.
Aaron, please go ahead.
Yeah, I had a question for Steve, and that's like, do you see like any difference in the size of the black hole? So is there any argument for why you would, because if you say you expect horizon scale modifications close to the horizon, that's a very different curvature scale for different sizes of black holes. So does the mass of the black hole come in at any point of the argument? I think is my question.
I'm not sure if I fully understand the question, but the idea, let me at least start off and then maybe you can rephrase. So, you know, of course, a natural parameter to think about for black holes is the Schwarzschild radius, which is roughly proportional to the mass. And so the idea is that the interactions would become important on those scales, and there wouldn't be some fine tuning. So say the interactions extend out to the event horizon, you know, they have to be present, so to speak, outside the event horizon to get information out. But, you know, one scenario behind the whole firewall kind of ideas is that the interactions extend outside the horizon, but only by a Planck distance outside the horizon. And, you know, that's kind of an unnatural fine tuning. So more natural from the point of view of the existing scales we have present, idea is that the interactions are present in a region of size of order the event horizon size, which also, by the way, there are good arguments that that's where the Hawking radiation is produced as well. So that's the suggestion. And so now maybe, well, so both mass and radius come into it, but how, can you maybe re-ask your question?
Yeah, my point is like, do you expect that phenomenon to happen for any mass scale black holes? That's
oh, yeah. No, I think it has to. You know, we need a we need sort of a, you know, black holes can exist for any mass scale, so far as we know, at least down to the Planck scale and up to, I don't know, cosmological horizon scales or something. And we need a resolution to the problem, to the crisis really, that is pertinent for black holes of any scale. And so that is a, you know, that suggests we should be looking for something that is universally present for all different size black holes.
Okay, so you expect it not to be tied to any scale.
Well, yeah, I guess you're asking whether, you know, maybe whether, you know, some effect is important for black holes, say at solar masses, and some other effect for black holes at, you know,
yes,
10 to the 9 solar masses. And in principle, it seems to me that, well, that would be more complicated, and it's, you know, just having one resolution to the problem is probably what we're after, and you know, having different phenomena that were relevant in different mass regimes would be surprising, I think.
okay, thanks.
Okay, I don't see any questions at the moment. I just have a very naive question for you, Hal. So your distribution or your distribution of like black hole spin, which was so for large masses so sharply peaked at very small spin, does that necessarily apply to primordial black holes or just to primordial black holes? Because I would think that if you have a stellar collapse, the star previously would have an angular momentum. So wouldn't that be carried over to the spin of a black hole as well?
Yeah,
it's very
I
naive.
mean, no, that's exactly why that distribution doesn't apply to that to stellar collapse. So the distribution doesn't violate any conservation laws, right? So if you're starting with a mass distribution that has a large angular momentum and it collapses to form a black hole, of course it's gonna some of that will be radiated away in gravitational waves, but most of it will remain in the distribution. You'll form a rotating black hole. So, so the point is that stellar collapse, it has a very particular history, right? And that history includes the initial state of the matter distribution, which is not distributed according to this microcanonical distribution at all, right? That history spun that mass distribution up. But yeah, the argument that I gave at the very end was too short, but was an attempt to argue for why this distribution could apply to primordial fluctuations. And the idea there is that it's actually a very weak condition on the initial state of the primordial fluctuations. It's just that that primordial fluctuation is nearly constant over the mass shell that leads to this distribution.
Okay, thank you. And because you have to run in a few minutes,
I had one more question for Steve, if you
no, sure. It just
Okay,
you might disappear at some point.
After that.
Yeah, you might just disappear at some point. So I just would like to thank you again. And we don't, if you don't see you anymore, that's totally fine because you have to run. But you will be with us for some time. So thanks again for your great talk.
Yeah, thank you. Steve, I was surprised and interested with the facility with which you dismissed microscopic remnants. So I wanted to ask you about the long time evolution of black holes. So if I form a stellar mass black hole, then I'm curious about the interior geometry and what you think of the interior geometry. If I form it by collapse right now, it has one interior geometry. But if I form it and if I form a 10 solar mass black hole and let it evolve down to a 1 solar mass black hole, the interior geometry is very different from the immediately formed 1 solar mass black hole. And that difference strikes me as important for this argument of whether microscopic remnants are really going to be abundantly produced or not. Again, for this historical reason, I was just giving as an explanation for Sebastian's question.
Yeah, so let me be careful here. The reason I think the discussion of microscopic remnants is one to have, but one that's hard to have now. And I've actually had various talks that have been derailed by such discussions, which is why I kind of tried to draw a hard line. I don't want to get too far into that discussion right now. But there is a fair amount of history. There were various models proposed back in the 90s where people made proposals that, complicated interior geometries, say very big interior geometries, et cetera, could suppress that kind of production and, spoil the argument that you get, basically huge production probabilities, total production rates. And, a lot of that was looked at pretty carefully. There was a lot of discussion back then. And in the end, I think we more or less coalesced on this view that infinite or unbounded production is a problem. So what I would say is that, and I know that there are various folks raising this set of questions again, and I would just urge those folks to really carefully understand the arguments that have already been gone through in the past and come back and say, well, okay, here's a problem with that argument. Why doesn't that argument hold? Because there were some pretty solid, in my view, arguments put forward. And that's where I don't want to get into all the details of that here. But just to mention, one argument involves production of pair production of charged black holes. And if you have a huge number of states for neutral ones, you're going to have a huge number of states for charged ones too. And that's an even more controlled situation, which we looked at. There's some long history there, and I don't know the best format in which to have that discussion, but it is a longer discussion where there's a lot of history there. And then, the question is, can something new be said to find, say, a loophole in the arguments that were given?
I've always been unsatisfied with the treatment of the interior geometry. I mean, that's why I was picking that point out specifically. But so like the two references you mentioned, you're happy with their treatment of the interior geometry?
No, there were other references which delved more into the question of interior geometry. There is a question of what you mean by interior geometry, of course, because we know things are looking pretty uncertain with say the structure of general relativity down near the singularity. But one of the messages is just to maybe succinctly say it, if you have some kind of Planck scale remnant, whatever the interior states of it is, let's not even describe an interior geometry. There's just an interior states, and there's a huge number of them, unbounded. Then, production of such things is governed by, well, if you believe in the quantum mechanics is part of the story, and that's what we're trying to save. So it's governed by quantum mechanics. It's governed by the fact that that's a local object. It's governed by the fact that we know the low energy coupling, say, of gravitational fields to that. That's what it means to say it has a mass. And those kinds of simple arguments, whatever its internal states are, seem to be essentially sufficient to give you this unbounded production kind of argument. Again, it's clearest in the case where we have the charge remnants or whatever, but anyway, there's some longer discussion we could go into, but there actually were models where you had complicated interior geometries, but those complicated interior geometries didn't prevent, say, infinite production. So again, longer story.
Yep, understood.
Hal, can I maybe also quickly ask you a question?
One. Yeah.
So you had these two populations, the one with one generation, and the other with first generation, second generation. Do you have an estimate for how these populations relate to each other? So the weight of the two populations?
Sorry, what is it about how they relate that you're curious about?
So how many of the red ones do I have compared to how many of the blue ones, and why?
Good. I understand. That's a very difficult question that ties to the point that Steve made, that if these indeed are due to primordial fluctuations, then we have to evolve these over the entire history up to when they merged, right? And that's not something that I've tried to do. The LIGO collaboration has worked on that problem a lot, and there is interesting results there. Although I think, Aaron, if you were to read this plot very literally and say, okay, Hal maybe is successfully explaining 3 1G 1G mergers and a lot of 1G 2G, no, that makes no sense, right? As I was saying, you can't view this plot as being an explanation for all of the LIGO data. I don't think it makes any sense in that context. You have to view this plot as potentially explaining something about a subpopulation of the LIGO data.
Okay, great. Thanks. That makes sense.
Thank you, everybody. I am going to run. I'm so sorry to do it, but I really appreciate the opportunity.
Yeah, thank you, Hal, a lot, and good luck. So Steve is going to stay a little bit longer, and I know Elle has a question, but all others, if you still have a question, please raise your hands.
So, Steve, you were saying that a lot of the proposed models with remnants, or even some of the non-remnant things, a lot of them show non-locality as one of the effects. And I was wondering what you mean by non-locality, because as Hal was saying, in some sense, non-locality is very natural in a gravitational system, which is why then we get that entropy is no longer extensive. And so.
Yeah, also a good question. So let's start with how we would formulate locality versus non-locality, say in a gravitational background, and then we could try to add gravitational back reaction. But I have in mind the basic statement that in a gravitational background, there's no communication of information outside the light cone. So, if we consider field theory evolution on the background and say we act on the state over here, then there's no manifestation of that effect at space-like separation, somewhere else. Now, of course, when we include gravitational back reaction, clearly that is modified, because if I act on the state here with an operator that creates, say, a particle of mass m, well, really in gravity, I should have a gravitational field extending out basically to infinity that by which I can measure that mass m. So it becomes a more subtle question, and this is the this question of how to think about subsystems. But at least, let's start with sort of the classical or semi-classical level. There are arguments that if you have, say, a region and there are different sort of matter configurations I can put in that region with the same gravitational field outside. Okay. So there can be localized information in that region. Again, let's think about it just at the classical level. There can be localized information, which I can't tell the difference between one state or another from measuring the gravitational field outside. I can only measure the total Poincare charges. And then if you want to state, coming back to, well, that's sort of localization. What locality means, it means that, that information, say, doesn't transfer outside of the light cone, is a rough idea. So that is something we really ought to better understand in gravity and the full quantum theory, and something we're working to do. But it's pretty clear how that operates, again, at the level of field theory evolution on a background. And, that's been the basis for a lot of the arguments for, say, what would be very, very surprising about, say, massive remnants. And the issue is, once, let's say you form a black hole, and then you want to explain some scenario by which a massive remnant forms, well, that black hole has some information inside of it. And somehow, for that information to sort of get out of the black hole and produce some new object outside the horizon, basically that information has to evolve in a way that, is evolving outside the light cone to get outside the black hole. If you try to draw that diagram on the classical black hole geometry, it's a diagram where you have to draw what looks like non-local or outside the light cone communication. So that gives you a flavor of the kinds of arguments and, well, that one encounters. But maybe a better way of saying it is, we don't fully understand what locality means in gravity. We do understand what locality with respect to a semi-classical background geometry means, and we need some surprising modification of that for a lot of these scenarios.
Okay, great. So actually, it's non-locality means communication outside the light cone. So maybe it's more like a non-causality.
Yeah, well, again, I come back to, sort of the definition of local quantum field theory in the algebraic sense. And, when we put in the locality postulate in quantum field theory, say if you read Hogg's book, the locality postulate is basically this commutativity of observables outside the light cone, which really is it's a statement also about, it's a statement about localization, but also about communication, that you can't send signals outside the light cone. So that sort of micro-causality statement is how locality is put in as an assumption into local quantum field theory.
Okay, so Is there any last questions from the audience? I still don't see any. Now is your
Or
last
any
chance.
first questions from
Oh.
the audience?
It does not seem to be the case. So let me now officially close the seminar and the series. And I would like to thank both Steve and Hal again for this great conclusion to the series. These were two super great talks. I'm really grateful. And you had a very great discussion going on. To all of you who are still here and who have missed the previous talks, they are available on our website or on YouTube. We've also posted the links to the Slack channel where you can post, if any questions would arise now after the talk is over, you can post them there. And it's also then time to tease the next season. So we're working on the third season, which will be a bit more foundational compared to our observational and phenomenological series, so we're going to talk about the measure in quantum gravity and topology change. And we're currently planning what kind of topics and what kind of speakers we are going to have. So hope to see you all and hopefully many more people back in fall for the third series. So thanks again to Steve and Hal and also the audience for listening for this second season.
Thank you.